Okay, let's continue with the projective algebraic sets. Remember, what did we have? Projective an irreducible algebraic set in the projective space. We said as algebraic variety, and last time we discussed this also at the end of the lecture. We discussed if we have an algebraic set in Pn. Let me change this color. So if we have an algebraic set in Pn, we define this con over V as the set. Namely, if you look at this definition, it is the, you remember the algebraic set is a subset of Pn. That means its elements are lines in An plus 1. So you take all the unions of those lines. For example, if we have this point 1m, then in P1, in its con is the zero set of this polynomial. So this is the 1 point set P, for example, and the whole line is its con over that point by definition. Okay, let's give another example. So in the same way, let's consider this set V as 1, for example, and 1, 2, for instance. These 2 points. So this is an algebraic set in Pn, P1, sorry, in P1. So this corresponds to 2 points, 1, 1, 1, 2. So it is this line. So this line, for example, and for also let's also include 2, 1, 3 points. V consists of 3 points. So this point, that point, let's say this point. So 2, 1. So name the class of this 2, 1. So that is this line. So it has 3 elements, and its con over V is the union of these lines in R2. Here we take field to be R. Well, in general, our field will be algebraically closed, but this is just an illustration. Okay, and let's see what we have. What else do we have? Yeah. Also, if we have, if we take an example, let's say another example. If we take f of xy is x minus y, then it is zero set of f is A's such that in P1, that is such that A is not 0. This is just the point 1, 1. Oops, 1, 1, AA or 1, 1. They're the same point. So, and the con over this VF is the set of all A's such that A is in K. Now A might be 0. the A might be 0. Okay. There's a second example, and another example. If we have, let's say, f of x, y, z is equal to x squared, y squared plus minus z squared, so that in R3, this is its graph is something like this. So this will be the zero set of this polynomial. And if you think of this as a zero set in the projective space, it is, let's see, how do we represent this? So if you look at P2 like this, so on the boundary, antipodal points are identified, then its intersection with this, the lines, the points of the projective space will be this set. That will be the V of F. The points, these points represents, and this cone is the cone over VF. Okay. So cone over VF, and so with what did we have above? Cone. Give me, yes. Cone over VF. Next is if oops, let me change colors. If V is not empty, then it's ideal of the cone over V and the projective in the project the projective ideal of in the projective space. The ideal of V, they are the same. And how do we show this? Let's write this as a proposition. How do we show this? So remember, CV is the set of all A1, AN are plus 1 such that either A1, AN plus 1 is in V, or it's 0. A1, AN plus 1 is equal to 0, 0. Okay, that was it. So let's take a, so this is the left-hand side is an ideal. Let's take a polynomial from this ideal A CV. So let's show that it is in IPV. How do we show that? So let P be a point. P, let's say A1, AN be plus 1 be a point in V. Show that for every representative of P, f of P is 0. So then A1, AN plus 1 is in CV, or also for any lambda, it's the line containing this set and the line containing this 1 n plus 1, A1, AN plus 1, the lambda times AN plus 1 is in CV for every CV for every lambda is not 0, even for lambda is equal to 0 for every lambda. So therefore, so since f is in the ideal of CV, then the color V, then this lambda times A1, lambda times AN plus 1 must be 0. So that means F is 0 on every representative, i.e. F is 0 on every representative of P. So therefore, by definition, F of P is 0, so that F is in the projective ideal of I. So that means we have AICV is inside IPV. Now let's show the converse. So let's take an element from IPV, and let's show that it is in, so that we have F, we may write F as Fm plus Fr, where Fi are degree I polynomial, degree I forms. We can write it this way. So in this case, all these Fi's are also in IPV because IPV is a homogeneous ideal, since V is a variety, algebraic set, projective algebraic set. So therefore, so let's show that this is Fi's are in this on the left hand side. So let's say A1, AN plus 1 be a point in CV. So it is either 0 or not 0. If A1, AN plus 1 is 0, then Fi of 0 is 0. The reason is that F is, since F is homogeneous. Since F is homogeneous, this is 0. So that means, yeah, F of I is equal to 0. And also, if this is not 0, if A1, AN plus 1 is not 0, so that means this A1, AN plus 1, by the definition of CV, this is in V, that's in V. So that since Fi is a is an element of IPV, and this point is in V, so that Fi of this A1, AN plus 1 is 0. So in fact it is 0 on every representative. So in particular on this A1 and AN plus 1 is 0. So that means F of I. So F of I is in F of I is 0 on every point of CV. So that F of I is in the defined sense in the ideal of CV. So that therefore. So for every I, of course, so that F is F1, Fm plus blah blah, F of R. This is in the ideal of CV. So therefore, projective ideal of this projective set is ideal of this projective set V is subset of AI CV, so that they're equal. Okay, that's the end of the proof of the proposition. Did I say proof? Here, I should say proof. Yes, proof. Okay, next. One more. We have this C is, let's see, like this. one more equality. It says, suppose I is homogeneous ideal. What did I use here? Where did I use the fact that V is not empty? If V is not empty, then CV is not empty. If V is empty, then CV is only 0, right? CV is only 0. So I believe that case. You should think about it. Okay, next. Suppose that, so let me write as a proposition again. Proposition, if I is a homogeneous ideal, such that it is 0 set is not 0, is not empty. In this case, if we look at the 0 set of the ideal and take the cone over that point, this set, it is, we can think it this way, or we can think of the 0 set of that ideal in the affine sense. So they are the same. This is in the affine sense, this is in the projective sense. Okay, here's proof. Let's prove this. Let's prove this statement. Okay, let's take a point from the left-hand side. Bunu çektiriyorum. So let's take a point from A1, AN plus 1 from the left-hand side, the cone over VPI. Okay, so that if all AIs are 0, then so before this, so I homogeneous ideal, so that I is generated by finitely many, let's say F1, F are finitely many forms. Fi's are forms. Let me write these GIs. So not necessarily degree. This is degree 1. So, oops. This is G1, GR. So the finitely many forms. GIs are forms, but not necessarily of degree I. Okay, if for all AI is 0, then G, let's say J, for any J, let me write J here. For any J, DJ 0, 0 is 0 because the G, all GJs are homogeneous, so that this is 0. So that means G, that means 0, 0 is in the 0 set of every generators of I, so that it is in this set. So if one of them is not, if one of AI for AI is not 0 for some I, then this A1, by definition of CV, AN plus 1 is in VPI. Okay. Now that's in VPI. So let F be a polynomial. Let F be a polynomial in a bit generator. So let Gj be a generator. Then since this V1 so the Gj of A1, so lambda times A1, lambda times an plus 1 is 0 for all lambda. The reason is that G is homogeneous, and also this point P is a 0 of Gj's. So in particular, what we have. In particular, so that means so the reason is that since Gj's are let's see, in VPI, yeah, yes, that's the reason. So that means in particular Gj A1 an plus 1 is 0, so that this is for all j, so that A1 an plus 1 is in the 0 set of I. Therefore, we have the cone over VPI is a subset of VAI. Okay, and I will leave the rest to you, and you should show that VA of R is inside the cone of VPI so that they are equal. Okay, I will leave that part. Next. So let me remind you what is, so let me remind you, affine Hilbert Nullstellensatz. What was it? Remember? It was saying that there were Nullstellensatz. Let me write like this. There were two pieces. If I is a kx1, let's say xn plus 1 is a proper ideal, then it is 0 set is not empty. And the second part was that if A is an ideal, if I ideal, where here assume that K is algebraically closed, then you look at the ideal of first 0 set of the ideal I, and then look at the ideal of that set that is not equal to I, but that's equal to the radical of I. Okay, that was affine. More precisely, this is affine Nullstellensatz. Now we will do the projective version of this. Projective now. Projective Nullstellensatz. So suppose I is an, let I be a homogeneous ideal. Homogeneous ideal in kx1 xn plus 1. then 1. This zero set of projective zero set of I is empty if and only if there is an integer n such that I contains all forms of the degree n plus 1 or greater than n plus 1. Because if it contains the degree of forms of degree n, all forms of degree n, then it contains all the others as well. Just multiply. Okay. Second, if this zero set, projective zero set, is not empty, then if you look at the ideal projective zero set and then look at the ideal, projective ideal, of course, projective ideal, that is equal to the radical of I. That's equal to the radical of I. The proof of the first one. So first of all, the followings are equivalent. The followings are equivalent. The first one is this VPI is empty. Second is VAI is inside 0, 0. It's either empty or 0. It contains only 1.0. And 3, the radical of I is equal to the VAI, and that contains x1, xn plus 1. And the 4, this x1, xn plus 1 to the n, the n power of this ideal is the subset of n, the subset of I. For some n. So how do we, why these are equivalent? So let me see the equivalence. Let me comment on this a little bit. So let me comment here. So so I implies 2I. So for instance, if VPI is not 0, so we put it this way, if VPI is not empty, so that means we have a point and then it contains a point A1, AN plus 1, VPI. Then all the points lambda A1, lambda AN plus 1 are in the zero set of the ideal, in the zero set of the ideal. The reason is that I is homogeneous. So therefore, it is infinite. It contains more points, so that this implies 2 implies 1. And if this is, and this way, also 1 implies 2, How do we show this? If VPI is empty, then VI, how do I show this? If VP, if that's empty set, yeah, the reason is that if it contains, if VA, let's think it this way, if VAP, say I, contains some point other than, if it contains some point other than 0, 0, then an plus 1. If it contains another point, then this is not 0, 0, say. Then that means for every generator of I, so if you take a generator of I, then f of A1, an plus 1 is 0. Moreover, since f is homogeneous, f of lambda A1, f of lambda an is an plus 1 is 0 for every lambda. So that means the point P, A1, an plus 1 is inside VPI, so that this is not empty. Okay. So we proved that, yeah. We proved that VPI is not empty if and only if VAI contains some point other than 0, 0. Okay. And 2 implies 3. Of course, this is by, so we assume that here we should assume that field is algebraically closed, although we didn't say before, for example, to complex numbers. So how do we show that 2 implies 3? Let's see. So if you look at x1, some xi, if you look at some xi, yeah, oops, sorry, like this, sorry. So let me prove for this way. If the radical of I contains x1, xn plus 1, then the 0 set of radical of I, which is the 0 set of I, is contained in the 0 set of this polynomial, xn plus 1. But the 0 set of this this ideal, but the 0 set of this ideal is just the point 0, 0. Okay. So that VI is inside the subset of VI is a subset of 0, 0. So it's either empty or it contains just 0, 0. And the other way, 2 implies 3. Let's look at this. So let's see whether x1, xn is in the radical. So let's look at xi. For any I, xi so let I could not figure it out yet. I wrote here something. So suppose x1 so how about this? If x1 xn plus 1 is inside the radical of I, so that, for example, some xi is inside the radical of I for all I is inside the radical of I, so that xi to the n for some n is inside I for all I again, so that if a1 oops, well, I want to show this. I'm doing the wrong thing. So let's assume this. So we will show this. Okay, I will. What did I do? Okay, let me leave this to you. I did, but now I don't want to spend more time. And 3 implies 4. Three implies 4. So if, let's say, j x1, so that j is equal to x1 xn plus 1. If this is inside the radical of I, then we show that there is an n. We showed this before. This is one of the problems. Problem 2 point something, 2.41 yes. There is an n such that j to the n is inside I. So that's the 4. And conversely, 4 implies 3. So suppose x1 to extend to the n is there. If x1 to the n, xn to the n, xn plus 1 to the n are in I, so that means xi's or x1, xn's, xn plus 1's are in the radical of I, so that in particular the ideal generated by them is a subset of the radical of I. And that's it. And for the proof of 2, if you look at IP, so let's remember, recall, let me write okay, so I will leave this, this time is up, so I have to finish it. This IP VPI is a ICVPI. That's equal to the AI VAI. It follows from the radical of I. This follows from the above two lemmas and the Hilbert Nullstellensatz. Okay, about position, proposition, and Hilbert affine Nullstellensatz. Affine Nullstellensatz. Okay, let me finish here. Okay, next time I will continue.